In this final video lecture for this week, I will extend the previous results on lack of uniformity to the lasso and look at the practical implications of that. Well, the lasso we can analyze in the same way. Now suppose first we just take an intercept and do the lasso on that. Well, we know with only one regressor, we just end up with the soft thresholding estimator. Now we have also there a thresholding, like for the hard thresholding estimator. So you can imagine that doing exactly the same steps, you can reach the same conclusion. This is covered in detail in the paper, and we're also going to do that a bit in one of the exercises. So for the lasso, we have the same problem that uniform convergence does not hold. And in fact, you have that for any kind of thresholding estimator, including, for instance, the adaptive lasso, which we can also write in that form. Now, let's look at the case where we have multiple regressors, because there the problem becomes slightly different. Dave and Butcher in their 2005 paper look at a general model selection setup where they have a regression model with two explanatory variables, x1 and x2. And x1 is the one of interest, so we do inference on beta 1. x2 is a control variable, and we don't know if we should add this control variable to the regression or not. And we're going to use some way to determine first some model selection procedure if we should include it. So that could, for instance, be take an information criterion, do the lasso, or do a hypothesis test. First fits the joint model, do a hypothesis test of significance on beta 2, and if it's not significant, you re-estimate with only x1 as an explanatory variable. Now, of course, this is an artificial case because, well, if you would only have two variables, you would typically just be on the safe side and put it in. But this, of course, represents the setting where we have many control variables to choose from, possibly even high dimensional. Now, in this kind of case, you could again use consistent model selection arguments to use oracle properties to say, well, if my sample becomes large enough, I will pick the right model, either this one in or out, with probability 1. So why should I care about model selection? Well, obviously what we can do here is do the same thing as before and take now our beta 2 as a sequence decreasing to 0 and show that if that is the case, your model selection criterion, no matter which one you choose, will have problems getting this part right. So we're going to make life hard again for our model selection criterion. And now the consequence of that is going to be felt through omitted variable bias. So omitted variable bias, of course, is a very old concept, and it's one of the first things you learn in your first econometrics class. If you leave out relevant variables out of your model, your regression model, and they actually are correlated with other variables, then your estimates will be biased. So we're going to have a quick look and recap that again, why this is the case, and well, make some standard assumptions. We have some correlation rho between the regressors x1 and x2, and of course our regressors are going to be uncorrelated with our epsilons for a correctly specified model. And then we're going to look at what happens if I leave out x2 from my regression. So we're going to do my regression of y on only x1. And well, in that case, of course, I can put the contribution of x2 into a new error term, epsilon tilde. Now, this error term is going to be the problematic one because this error term here has x's, and x's are correlated with other x's, and that will create an endogeneity problem and therefore the omitted variable bias. So let's write that out and see where we end up with. So we write out the least squares estimator, and then we plug in. We only have one variable, so we don't need to do the matrix notation. And then we're going to plug in for y the x1 times beta 1 plus the new error term epsilon tilde. Well, then we see that we get x1, x1, so x1 squared. So we have sum of xi1 squared. We have sum of xi1 squared in the denominator. They cancel out, so we're just left with beta 1. And then we have the other parts. Sum of xi times epsilon tilde divided by sum of xi squared. Now, that's all, of course, standard so far. And if this epsilon tilde would not be correlated with your xi1, then you would not have any problems. But we can write epsilon I tilde as the original epsilon I, which is indeed not correlated with xi1, plus the omitted part, the variable that we omitted, xi2 times beta 2. And then we see that when we then write this out again, because we're going to now write it out in two parts, well, we have the part that we should have, the familiar part, which is the safe part, right? There's no correlation here. And this will give us actually our normal distribution if we apply the central limit theorem. But we now get this additional part, which is about the relation between x1 and x2. So this comes actually from here. Well, and this thing, that we know that it's going to converge to the covariance between x1 and x2. So we're going to have the coefficients that we had there, that we assumed here. So the expectation of x1 times x2 is just sigma 1, sigma 2 times rho. Rho is their correlation. So we have beta 2, which comes from here, times rho times sigma 1 times sigma 2. Well, you see you can cancel out 1 sigma 1 against 1 sigma 1 in the denominator. But what we have is that this thing converges in probability to something which is not the same as beta 1. So we have a bias, and the bias in fact persists asymptotically. Now, this is all, of course, standard, right? We know this from our basic econometrics classes. Now, consistent selection tells you that, well, it's not a problem, because if your beta 2 is large enough, you pick up the right model. So beta 2 here, if it's large enough, you would have picked it up, you would not have estimated this, so this term would not have been there. So it's only there if beta 2 is small. But then you might say, well, if beta 2 is very small, then this part will also be very small. But the problem is we can go sort of in between by choosing a rate like this, gamma divided by square root n, and that will be too small to detect, but large enough to cause problems and not disappear. And so we have again a case where we get a pointwise limit that is not the same as uniform limit. So we don't have uniform convergence in this model. To see what this actually means in practice, let's do again a small simulation study. So I'm going to take a very similar DGP as before, where I take a linear regression model, and I'm going to take most of my betas to be 0. So in fact, everything up from beta 3 up to higher. So I go up to 10 variables, and 3 up to 10, all the betas are 0. Beta 1 is 2, and I'm going to vary beta 2 between 0 and 2. So I have one relevant variable, I have 8 irrelevant variables, and I have one that is sometimes relevant, sometimes not, and how relevant this depends on which values I take. For the rest, I take a very simple setup. I assume the standard normal error terms. My x's are generated as normal with certain correlation rule. I'm going to do again Lasso kind of methods. I'm going to do BIC for selection, and I'm going to do the treatment setup as I had before. So x1 is my treatment variable, my variable of interest. I want to do inference on beta 1. The other variables, I don't know if I should include those as control variables or not. So I'm going to use the lasso to decide on that. So this very much matches the setup of Leib and Butcher, except where they only had x2, I have x2 up to xp. And so now what the theory tells me is that things should go wrong, if indeed it's so important to have uniformity. If it's not so important to have uniformity, things might actually still turn out okay for larger n. So let's have a look at what happens. Now, this is the first graph where, again, I do lasso, adaptive lasso, and post lasso as before. And what we see here, well, most of the functions of the estimation methods gives you results quite close to 95%. So again, least squares is completely unaffected by the value of beta 2. Well, by now we can explain that because least squares, as mentioned earlier, automatically gives you uniform results. Well, that is something that we see here. The other methods are not too bad, but they do have this blip here around beta being 0.4, 0.5. The methods drop, which in itself is maybe not too dramatic, but on the other hand, it is a bit weird that we have this drop here. Now let's increase the correlation from 0.5 to 0.8. Well, suddenly the drop becomes a lot more pronounced, and now we can also not say it's not problematic anymore. Right? We go below 0.5, so our interval, which should cover 95% of the cases up here, it's now only covering 50% of the cases. And the interesting thing is, and that matches the theoretical analysis that we do, is we see this drop appearing for smallish values of beta. So it's not at 0, there it's okay, but when you move away from 0 it gets worse. And then when beta 2 becomes large enough to get picked up, it becomes okay. And we now have the tools to explain this. Right, so if we're at 0 or very close to 0, then beta 2 is so small that the omitted variable bias that we found here is going to be very small, because beta 2 is just going to be very small. So, well, that will not be the most problematic case. Now, if beta 2 is very large, then that bias could become large, but will never end up in the case where we don't estimate it, because there our model selection criterion will be able to pick beta 2 up. But in between, we have this drop, and this is a significant drop that is important. Now, let me increase the sample size to 100. So here I have 150, here I have 100. Note how the drop here gets deeper. It's here at 0.4. So I'm going to keep my cursor on it, and you see that it's a lot worse than it was in the previous slide. It also becomes more to the left, so we tend to be better at picking up moderately large values of beta than we were in this case. But at the same time, with this becoming steeper, that is clearly a cause of big concern, because that would indicate that even though it's in a narrower range, we actually are, if we are in that range, we're doing worse. And again, the key issue is that we have no clue whether we are in that range or not, because we have no clue what the true value of beta 2 is. So it seems that actually, when you do simulations, these things do show up. And we might at first say, well, we dismiss all of this talk by Lip and Butcher and their papers for just being of theoretical interest and no practical relevance. But you don't want to end up here with an interval covering only 40% instead of 95%. That's very undesirable, of course. And you might, right? You have no clue. Maybe beta 2 is indeed equal to 0.4. Maybe not. That's what we don't know. So we would like to counter this. But now there is another problem. And Lip and Butcher make that aware to everyone, where they show that actually the correct distributions of the post-model selection estimators, like the one we derived for the hard thresholding estimator, that you cannot estimate those distributions consistently. So otherwise you could just say, okay, if I know that distribution, I will just use it in my analysis. But that's the thing, you cannot do that because you cannot estimate it. So we seem to be in a situation where we're screwed. Our intervals don't work. Our post-selection intervals have poor coverage for the right parameter values or the wrong parameter values, if you prefer. And this does not seem to be an easy fix. Well, one fix would be the beta min conditions, so having betas large enough. Yeah, but of course, there's no reason in general why we would believe that to be realistic and that to be true. And now we've only looked at a case where p was small. In the simulations, p was 10. So we have not even looked anywhere near the really large high-dimensional cases. Well, obviously, if you would do the same kind of analysis there, the effect would be much worse because you need to do much more selection than here. And so people have realized that, well, yes, I mean, this is indeed true, and we should not rely on oracle properties or beta min conditions in practice anymore. So what we should do is acknowledge that there is a problem here. And the good thing is, when people started to acknowledge that there was a problem, they also started coming up with solutions and with answers to that. Now, this of course will mean that we need to look at things from a different perspective, because from the standard way of looking at it that we did so far, we will clearly not be able to find a solution. Now, thankfully, there have been quite some methods proposed in recent years which address this issue of doing first model selection and then doing inference on the resulting model. So this is what we're going to do in the final weeks, where we're going to have a closer look at the work that has been done on extending these kind of settings and finding actually methods which do allow you valid post-model selection inference. Now, of course, because it's impossible to estimate the distribution of these post-model selection estimators, they are not direct methods, but they're sort of methods which say, well, what if we would tweak the problem, or if we would change the problem a tiny bit? Could we then actually get such an answer that we are looking for? And indeed, it turns out that you can. And this is now, I think, one of the most exciting fields in statistics, where a lot of stuff is still happening, and a lot of contributions have been made over the past few years. And I will start covering this next week.